Hi everyone, my name is Kyle Roberts. I work for JEI Structural Engineering, and today I'm going to give a presentation on aluminum composite panels. As an overview of what we're going to be looking at in this presentation, we're going to start with the design loads. So what are the loads that we look at for panel type projects? And then we're going to look at a panel analysis. So what goes into the panel analysis itself? And then we're going to dive into the anchor analysis. So how do we get the loads from the panel through all of the components to the main structure? And at the end, we're going to look at some specialty situations where you may need special framing or special panel analysis done. Then we're going to look at disengagements of panels and what that means. And then we're going to talk about non-ACM panels briefly. So the biggest component that we really have to look at for design loads is going to be our wind load. And there are a lot of factors that go into the wind pressure analysis for a building. The footprint of the building, the height of the building location, wherever that is, and then what's surrounding the building. Is the building in a prairie, or is it in a metropolis such as Manhattan? Or are we next to the sea? What is going on? Where is our building at? All of those factors will play into what the wind pressures for a building are. There is one big one that is very important for everyone to understand, and that is the building occupancy or risk category for a building. There are four. One being the least restrictive, four being the most restrictive. So a category one risk category building you can think of as an agricultural facility. So maybe it's a barn that is storing farm equipment. If something would happen and it would fail, you have less worry about loss of life than you do a risk category 4, which would be your hospitals, your prisons, things like that. And this is important because if a contractor is trying to compare one project to another, they need to understand the difference between these categories, because if they're trying to compare similar building sizes and locations to get a bid prepared for a project, and the bid that they're comparing it to is a category 2 and the new structure is a category 4, your wind pressures for that new building are going to be higher. And what that can mean is what was done in engineering for the previous building won't work for the current one. You may need to have a smaller girt spacing. You may need to have stiffeners on your panel. You may require more fasteners. So it's important to understand doing a side-by-side comparison of buildings doesn't always work out. The wind pressure in a building is going to provide the suction on the panels, and it's going to be the primary loading for for deflection. It also is going to be the main provider of the tension that our fasteners. We also look at the dead load and live load of panels. The dead load is going to be the weight of the panel and all of its components. It's going to be slightly different between a 4mm panel and a 6mm ACM panel, but they're roughly about 3.5 psf per square foot. Occasionally, we will have areas on a building where we have an awning wraparound or parapet cap or roof panels where we have to take into account live loads. This is areas where potentially birds or small rodents, such as squirrels, can get onto the panel. Now, the majority of time, their weight is not going to be enough to cause significant damage to the panel, but there's always a potential that it could happen. And really, the concern would be overstressing an anchor load. However, the same situation, if you have an awning wraparound, you could have snow load. And snow load can be a large load. And there's two different kinds of snow load. So one would be your typical ground snow load. So for instance, you're out in an open prairie with no trees and it starts to snow. what is going to be that ground snow load of the snow that's falling. The second and more costly, if not designed for, is the drift load. So in a case where you have an upper roof, that snow from the roof can blow across over parapet and onto the structure below, in this case, a panel. And the weight of that snow could cause the panel to deform and permanently deform. That can cause a lot of issues. And these details in these areas need to be addressed early on in the project. Blocking, built-up girts, Z-girts, hat channels can be used to support the panel to not allow it to deform in that way. And this is crucial because the name of the game with snow and rain is to get that snow and rain off of the structure onto the ground as quickly as possible. Because if the panel does allow that sag, you could have sealant joints between the panels tear. You could have sealant joints between the panel and the main building fail, and water could get into the main structure of the building, and we all know that is a no-no. This is a big area where engineers and contractors really need to pay attention. And to give you an example, this is a sunshade that we've seen on a curtain wall before. And what we have here, you can see the lower sunshade, it has a smaller load. That's because it's shaded by the upper one. The upper panel, the upper sunshade is getting all of the drift load from the roof above. And what could happen is, in this situation, is you have a large amount of snow shedding off and landing onto a lower roof. And what happened in this case was the purlins failed. So the roof structure failed. And as you can see, the weight of the snow caused a massive deformation of the whole entire roof system. And now that roof is going to have to be replaced. It's critical to understand snow drift and to apply the proper snow drift in our calculations. So when we look at the panel analysis, we're going to be looking at the stress and deflection of a panel. From experience, I know on a majority of projects, it's going to be the deflection of the panel that's going to control. Not always, but a majority of the time it will be. The deflection criteria for a panel project is going to be found in the project specifications. Architects typically supply an L/60 or L/180 criteria. And what that means is you take your least width of a panel and divide that by the number below. So for a 60-inch panel, let's say a 5-foot wide panel, you're going to get a deflection limit of 1 inch if you're using L/60. However, if your deflection criteria in this project specifications is L/180, you're going to get 1/3 of an inch, 60/180. That's a big difference. So the more restrictive that bottom number is, the higher it is, the more restrictive the deflection criteria becomes. The IBC lists L/60. So you're never going to see an L/50 or an L/40. The IBC lists an L/60. What the IBC also gives engineers is a tool to help reduce that deflection. They basically say, for the purposes of deflection calculations for a panel, you can take a 0.7 reduction for allowable stress design for the panel. As engineers, we can take another reduction based on the area of the panel. The larger the panel, the smaller the wind pressure will be on that panel. We can combine both of those to calculate a reduced deflection. Sometimes that works and we get under the design deflection, but not always, and stiffeners will have to be utilized. Now, in the case of stress, this is a graphical image, if you will, showing the difference between a two-sided supported and four-sided supported. And what you see is the stress zone, that pink zone, is much larger for the two-sided supported than the four-sided supported. What you also see is the deflection of a two-sided supported panel is much larger than a four-sided, about a ½ inch larger. It's JEI's recommendation that all panels be four-sided supported. So if stress and deflection both don't work out, or one or the other doesn't, we have to add stiffeners. And stiffeners can open up a new can of worms. They do their job, they stiffen up the panel, and they reduce the overall deflection and the stress. However, stiffeners can then become the controlling factor. Stiffeners are essentially beams, and they're inherently weak due to their size. So when we look at the stress and the stiffener itself, that can be the new controlling factor of the overall panel and may require more stiffeners to be added. But this is a good time to talk to the architect, because stiffeners bring an architectural blunder challenge with them: oil canning effect. So essentially, you adhere the stiffeners to the panel, and over time you will see from the exterior of the building little areas where the stiffeners are. That's called the oil canning effect. And sometimes you can have that conversation with the architect and say, my engineer's done everything, stiffeners are still required, and I just want to let you know because oil canning could happen down the road. And the architect may go, well, what do we need to do to prevent that? And then we can have the conversation of reducing panel sizes, changing the deflection criteria, what have you. So when we start looking at the loads of the panel, we really start to break down into more engineering analysis, deeper engineering analysis. So basically, we take a 45-degree projection down from the corners and divide the panels into halves. And what you get is these areas that we have shaded in red are going to provide load for the panel. So on the left side, those smaller little rectangular hatched red areas, those are going to be providing loads to the shorter side of the panel, where the right side is going to be providing the load for the long legs of the panel. Now don't forget, for these situations, you're going to have panels right next to each other, so that load's going to be doubled. This is very good time to talk about dead load. Let your engineer know what clips you're using. Detail them clearly in your shop drawings, because not all clips are made equal. And the clip shown below, it has a slotted connection. That slotted connection is not going to allow for the transfer of dead load from the vertical panel edge to the Z-girt, or whatever girt you have behind there, which means all of the dead load is going to be taken only at the horizontal joints. This is very important for your engineers to know. Be courteous and detail it clearly in your shop drawings. So we take those loads and we get our dead load and wind load from the panel. All of that has to go through every component, from the panel, through the rivet, through the perimeter panel extrusion, to the main extrusion, back through the girts into the main substrate. And a horizontal joint is shown here. You're going to have a load from the top panel and the bottom that are both going to be going into the main clip. That's going to provide you a total tension and a total shear due to dead load. One of the biggest headaches I get on projects is pryout of fasteners. If the load, your tension load is high enough, it will cause the fasteners to pull out of whatever substrate we're going into. Majority of the time, cold form steel studs. And similar to a hammer, you have a point of rotation, a point where you're going to rotate and pry out. In the sketch below, it's that red dot. And essentially, the tension load is going to take that angle and it's going to rotate it about that dot. And it's going to cause a tension load on that fastener. Now, as engineers, we have a capability of calculating if a pry-out load is actually going to be admissible. I'm not going to get into that here, but there are equations that we can do to help our clients out to say we don't have to take into account pry-out because the thickness of our girts are larger than the minimum based on the calculation. And that really helps out our clients by taking that extra step and doing that quick calculation. But if we have to take out pry-out, we have to take into account pry-out. So the two examples seen below, you have a built-up Z-girt and a channel. And you can see that the point of rotation from where the tension is applied is different for both. But the location of the screw from the point of rotation is the same, that 15/16. And what we see is for the longer the pry-out leg is, the larger the tension is. So if your tension, let's say, is 50 pounds, and in the left scenario, you have a built-up Z-girt or just a standard Z-girt that's 3 1/8 inches away from where the load's coming in, you could have a tension load that's 3.33 times larger. So for a 50 pound, it's going to be over 150 pounds at the stud, if that's what we're going into. So you can reduce that by changing the orientation from a Z to a channel or C, and that reduces your pry-out leg, which then reduces your pry-out. Which is one of the methods that we can do to reduce that pry-out. And I'm going to get into more in next coming slides why pry-out is such a big issue. But first, let's look at bending. So when we have Z-girts, a majority of the time what we see are Z-girts that run horizontal to the plane of the wall. So essentially perpendicular to the stud distance, or to the studs. And what that can cause is bending in the girt due to dead load. And we must look at that because every material, regardless of what it is going to have its allowable stress. And we check the allowable stress on all of these conditions for dead load and for tension. This can control the spacing of the girts. The closer the girts are together, the less load on the girts, meaning there is less stress within the girts. The farther apart they are, the more stress they have. Something that your engineer will talk to you about. There is, for dead load, a way we can get rid of the dead load. That is by running your girts in line with the studs. What that does is it takes the bending of the dead load away. Something to consider on your next project. So we just got done talking about pry-out, and here's why pry-out is such a big deal. Because if we have to take it into account, we typically need more than one fastener. Sometimes we need rows and columns of fasteners. Well, a cold form steel stud is only about 1.5 inches to 2 inches wide, so that limits how many fasteners we can actually get in there. And then the stud thicknesses, the gauge thicknesses. An 18 gauge stud is less, it's only 0.0451 inches thick. A 16 gauge is still under 1/16 of an inch at 0.0566. But what the real caveat is the pullout. So the thinner material, the less pullout value you have. And we need the pullout value to resist our pry-out tension. So as you can see, for an 18 gauge stud, it's about 144 pounds. 16 gauge studs can come in either 33 or 50 gauge or grade. And you can see that for a 33 grade, you get 180. For 50 grade, you get 260. So about a, what is that, 80-pound difference by increasing from a 33 grade to a 50 grade stud. These are for quarter-inch values. If you try to use smaller fasteners, a number 12, number 10, you're gonna reduce these even more. So the recommendation is the thicker the stud and the higher the grade, the better. So in your bid phase, have that conversation, say, hey, can we get minimum 16 gauge studs? Sometimes it's an easy, sure. Other times it's not. But you'll never know if you can get them until you ask for them. It will help you out when it comes to anchoring and reducing the number of fasteners on the project to have a thicker stud to go into. So let's talk about some limitations and weird stud configurations that you need to watch out for. This is what we consider an eyebrow framing. So you have a large projection out from the roof line, and you see a panel wrap around, go up at an angle, and come and wrap around the parapet. Watch out for these areas and make sure that the cold form steel provider is also providing the cold form steel in these areas. Because the framing in these areas can get very tricky and very costly very quickly. Just be aware of areas like this during your bid phase. Another area on this project that an engineer here at JEI did was we can't anchor into the beam. So we have to create a structure to wrap around the beam that we can anchor the panels enclosing the beam to. Watch out for areas like this because unanticipated framing will cost money. Specialty framing like this will cause engineering time and additional engineering analysis that will cost additional money. Just be aware of these areas. So what happens if we have a rain screen, aluminum panel, whatever it might be, a solid aluminum panel, an area where we don't have studs, maybe such as a parking garage? Well, you're going to have to use custom framing. And on this project, we had a solid aluminum panel that was going back to a aluminum tube that we had to design that was anchored into the perimeter spandrel beams of the parking garage, similar to what you would see in a unitized curtain wall. Design these because parking garages move. So just make sure if you don't have a structure to anchor into for the panel, that we're thinking about how the load will transfer back into the main structure. This project required a lot of back and forth and a lot of specialty engineering. Disengagement of panels is a big concern. And what we mean by that, this is a wraparound corner seen below. And what you have is the potential for wind on one face to suck the panel away from the aluminum clip. And what could happen in this area is, although it's still supported at the top and bottom of the panel, you now have an edge that has slid out from the panel extrusion and is now free. Potentially, it could, when the wind stops, slide right back into place. But there's always a potential that it won't slide back into place. And now you have an area where the environment from the outside can get into the void between the panel and the main building. We want to prevent that. And there are a lot of things we can do, from flipping details, from adding fasteners, things like that. It's just important to consider these areas because no one ever wants to go out to a project and have to take portions down to repair something like this. We need to address it up front before the project actually is installed. So there are specialty panels, panels that are not rectangular, that we have to get into and we see from time to time. These also might have openings or notches or something else. And these can cost a lot more because they create a more extensive analysis. And they create more time. They take more time to look at. So to give you an example, here's a standard non-rectangular panel. We have to use a special finite element analysis software, an FEA software. And that produces the stress and deflection that we need to do our comparisons for the allowables. And as you can see, it's a very complicated, very tedious model. It takes more time to do these types of modeling. A similar panel on the same project had a notch in it. And as you can see, this one has stiffeners. We had to stiffen up the edge around where the notch was to get the stress to work. And you can see the stress distribution along the whole entire panel. Specialty panel took a lot more time to get done. This one, we have a notch around a column, very similar to what we've seen on the other two previous, but just showing you it takes a lot of engineering skill, technicality, and whatnot to get this done. So there are other types of panels besides ACM panels that we see, from insulated panels to perforated metal panels, maybe not as extreme as what is being shown, but maybe panels that have a hole pattern or a diamond pattern or whatnot cut into them. We have the tools at JEI to look at the stress and deflection of these panels. We also can look at solid aluminum and steel panels. We've even done a copper panel before. And then there are the roof panels. And anytime you need help with any of these systems, ACM, insulated, perforated, or any solid or roof panels, let us know. We're here to help. So let's just do a quick recap. The smaller the span of the panel, the smaller the width of the panel, the less load onto the panel, less load onto the girts and fasteners, the better. It may reduce fasteners. The higher the gauge thickness of the studs that we are going into, the better. Shoot for a minimum 16 gauge. Watch for areas on the project at wraparound corners, soffits, parapet caps, where panels can disengage from the clip. And then watch for areas where specialty engineering may be required, or specialty framing, or special panel analysis, because that could drive up the overall engineering cost for a project. I hope you've enjoyed this presentation today and have learned something new, or maybe just got a refresher on some stuff. If you have any questions, comments, or you would like us to provide a quote on a project, please feel free to reach out to info@jeistructural.com. Thanks, everybody. Have a good day.